Hello, everybody. I'm recording this video for filters. So let's start. Have some. Okay. So let's first know what do you mean by filters? What is filters? Okay. Very simple. It's a circuit. So here you have a circuit here. Okay. And then you have different input frequencies. So we have here different frequencies. If so, at the input, we have different signals with different frequencies, F1, F2, F3, F4, and so on. And in the output here, actually what's happening is that's why we call it filter. Look at the English name, filter. So some of these frequencies are gonna pass and the circuit is gonna block. So this is the main thing here. So the circuit, let me make sure the recording is working. Yeah, it's okay. So here, that's why the circuit is called filter, because some frequencies are, the circuit is gonna pass some frequencies and also is gonna block some frequencies. Okay. In this experiment, I'm going to teach a very simple filter just to understand the concept of filters. For sure, maybe in the future, in other classes, you are going to design a more complicated circuit. So let's start to. So this is the definition of filters. Again, very simple. It's a circuit that can pass some frequencies and it can block some frequencies. Okay, based on the frequencies it can pass or block. We have different types of filters, okay, as we see here. The first one, we call it low pass filter. The second one, high pass filter, band pass filter, and then band stop filter, okay? So let's see how it works. So we can know how it works from what we call frequency response. So frequency response. So this one here is frequency response. So this plot can tell you which frequencies can pass and which frequencies the circuit can block. So as you see here, for example, here in low pass, okay, all frequencies starting from 0 until a certain frequency, we call it FC, or we call it cut off frequency. Remember this name, cut off frequency. So all this frequency should pass, okay? Any frequencies that greater than FC should block, okay? So again, low pass filter should pass any frequencies from 0 until a certain frequency. We call it a certain frequency. We call it, sorry, cut-off frequency, okay? If we see high pass filter, this is how it looks like. It should block all frequencies from 0 until a certain frequency, FC. And it should pass any frequencies greater than FC, from FC to infinity. It should work this way, okay? The third one here, we call it bandpass. So, by the way, the word band in communication, it means a certain frequency range. Okay, that's why we call it band. So here in bandpass, as you see here, any frequencies that is in this frequency range are gonna pass. Any other frequencies, the circuit should block them. Okay, this is very useful in communication because in communication, every channel has a certain band, okay? So if you want to receive a certain channel, you should know what is the band of, what is the beginning frequency, what is the last frequency of this channel, and then this filter can only pass this channel and it can block other channels, okay? Um, The last one, as you see here from the frequency response, it can pass everything except a certain range. Okay, guys. So again, you can see filter some frequencies circuits that can pass some filters. It cannot pass other filters, and sorry, it can't pass other frequencies, and it has many very useful applications. So in this experiment, we are going to only focus on low pass filter and high pass filter. Okay. So if the filter circuit is ideal, so if the circuit is ideal, okay, this is how the frequency response should look like. Again, this term is very important. Frequency response, meaning how the circuit respond to frequencies. Okay, so this is how it should look like. Okay, however, in for practical frequencies, it doesn't look like that practically. What happens practically is, as you see here, it's not gonna be sharp here at FC, but we're gonna have like somehow a curve this way. So as you see here, so it should be like a curve this way. Okay, so that means there are, although this is what this is practically, although I wanna base all frequencies until here, okay, and anything greater than should not pass. But however, what happens, actually the circuit is going to pass some frequencies here, okay, with different amplitude or with different gain. Okay, maybe this frequency are going to be smaller in amplitude, but it's gonna pass more filters. Same thing for this one, for high pass. So high pass means, or ideal high pass, so everything from 0 until FC it should block. But what happens, see, we have like some, as you see here, something like a curve this way. For sure, we wish if we don't have it, but this is practically how it looks like. This is ideal. So we try our best to make our circuit behave ideally. Okay? So as you see here, although I want to pass all frequencies from here to infinity, what happens because of this curve, we are going to pass some frequencies here. Maybe they have, yes, maybe they have different amplitudes, but still you can pass some of them. Same thing for the other one. So as you see here, instead of cutting the frequencies this way, we have a curve this way. Same thing here as well. Okay. So actually what happens in because this is this is just a very simple circuit for filters. So we're gonna have a very simple circuit, okay? But as I'm gonna teach right now, you should know that the more the circuit is complicated, the closer the circuit will be to the ideal behavior. That means as the response becomes very closer to the circuit will be better, okay, to the ideal response. The circuit is better. And not only that, but actually nothing is for free. So if you want to get a behavior or frequency response that's close to the ideal one, the circuit has to be more complicated. And this is maybe something you are going to learn in the future. This is just introductory experiment about filters, okay? So let's start with okay, so now you told us filters, it's a circuit that can block and pass some frequencies. But how this can happen? How this filtering operation can happen? What is the idea? It's a very simple idea, very, very simple idea, okay? Let's tell you what is the idea. The idea is that, if we have a capacitor this way, okay? As you know, this is the impedance of the capacitor. Impedance like resistance, okay, in complex domain, okay? The interesting thing here, if we compare it to resistance, so the resistance has the same value for any frequency. So the value of the resistors does not depend on the frequency. But it's not the case in case of capacitor. So as you see here, in case of capacitor, the impedance is 1 over J omega. Omega is actually 2 pi F times C. Okay. So so here it depends on F. That means if you have a capacitor and you have signals with different frequencies here, they are going to see different impedance, different resistance. This is a fact. I'm going to use this fact, or this is the main, underlying idea for filters. Okay, so that means for some, as we see here, If the frequency is very small, at very, very small frequencies, you can see here from impedance will be very close to infinity. That means it's open circuit. So some frequencies are going to see open circuits. They are not going to pass. You see what I'm saying? It's very simple idea. It's not difficult idea. You feel like the topic is difficult, but it's not, right? Because this is something naturally. As you see here, for very small frequencies, that the capacitor is going to act as open circuit. For higher frequencies, the capacitor should have, from this formula here, the capacitor should very close to zero, short circuit. That's how. So by using this idea and put the capacitor in a certain way, I can create a filter. So let's start with the first filter, which is very simple filter. We call it RC passive. Sure, I will tell you what we mean by passive. RC low pass filter. That's it. Look how it's very simple. Just one resistor, one capacitor this way. Input here, output here. Very simple idea. Okay. As you will see later, when I create a high pass filter, all what I'm gonna do, look, very simple. I'm gonna put a capacitor here and put a resistance here. So I'm gonna just switch the location of the capacitor and resistance, and this will create a high pass filter. Okay. But okay, can you explain how this very simple circuit is gonna work? How it's gonna block some frequencies? Okay, before I go to the math and I show you how the math work, let's just by intuition, let's think about it. In case of very small frequencies, okay, so this capacitor will be like open circuit. So that means V output should equal almost to V input. That's why this circuit is gonna pass. It's gonna pass low frequencies because the capacitor is open circuit. However, and at high frequencies, this capacitor should become like a short circuit. And now the voltage equal to zero. Very simple idea, you see? Anyway, but let's do it mathematically because I want to get equation. I want to know at what value exactly this happened. Okay, so let's do it. So what we're going to do right now is, as you see here, this capacitor has impedance, which is ZC should equal 1 over J omega C. Okay, so if I want to calculate the voltage V out in relation to V input, I can simply use voltage divider. So if I use voltage divider, so here V out equal to the ZC, which is like the resistance of C. It's not, again, we don't use the word resistance. Here we use impedance, which is actually acting the same thing like a resistance, divided by R plus ZC times Vn, okay? So this is a relation between input and output, and this is ZC, okay? It's just voltage divider, normal voltage divider. Now, I want to calculate something, we call it the gain. So the gain here is actually V output divided by V input, the ratio. Okay, and so the gain V out divided by should equal this value here. Okay, and then all what I'm gonna do, I'm gonna just plug in ZC here, and the final result is the gain, which is the relation between input and output, should equal 1 over 1 plus J omega C R. Okay, and for sure, this is a complex number. If I convert this complex number to the polar form, this is the magnitude and this is the angle. This is the magnitude and this is the angle. Okay. So why this is important? Because again, remember, what is this? This is the relation between V output and V input. You see what I'm saying? So here, this is the magnitude. Okay. So if this is really a low pass filter and it has to pass low frequency, so this magnitude has to be very close to 1, okay? Or in case, as you will see right now, in case of low frequencies. However, in case of high frequencies, it will be 0 or very close to 0. That's why V output equal to 0. Anyway, now, what do you mean by the angle here? This is the angle. The angle here should tell you what is a phase difference between input and output. So here, as you will see, if this is the input, for example, and this is the output, whatever, how. So if this is the case, so both of them are in phase. They have the same angle. However, this is not always the case. Sometimes, as you will see here in this topic, maybe this is the input, but the output is here. So in this case, we say, so look here, so the input already started before the output. So here we say the input is leading. We need to know what is the angle here leading. Okay, so how I can know if it is in phase, leading, or maybe the output will be here. So in this case, the output is lagging the input. Lagging means, the input is lagging. Lagging means comes after the output. Okay, you will see all of that. But this is the importance of. So now I have two equations. Okay, this one should tell you what is the value of output at different frequencies. This should give you the frequency response, as you will see right now. Okay, how the filter works, how this is the response we should see. Okay, because this is a low pass filter. So this circuit will show you how we will get a response like this one, where at some frequency we have a gain. Okay, or here is a gain maximum should be 1, but anyway. But in more than that, as higher frequencies, the output is 0. Okay, output of these signals of these frequencies are 0. And this one again tells you the relation between the phase input and output. You will see right now. Okay, so that's what I told you. So if you just if you draw this relation, and also if you draw this relation, that's what I told you. But let's talk about this one a little bit, because this is a very, for any filter, this is a very important plot. This plot, we call it frequency response. Very important, frequency response. Okay. One important thing here, what happens for this frequency response, we don't plot it in linear linear axis as usually we do. No, instead we do it. We use logarithmic. We draw it using logarithmic, as I'm gonna explain more in details. You know why? Simply because usually these frequencies are huge, usually, or if this number is so big. So if instead making like in order to capture better the behavior, okay, as I'm going to explain in details, usually it's better to do it on logarithmic um, uh, um, axis instead of linear. Okay, you will see right now what it means. That is why what I'm gonna do right now, instead of storing here, instead of using here, this is again this value. No, I'm gonna usually we calculate the log of this value. We call in decibel. We call it decibel. Okay, as you see here, we call it decibel. Okay, so I'm gonna take the same value we had before, but I'm not gonna use the exact value. I'm gonna calculate the logarithm of this one. Okay, and I'm gonna explain later why we do that. Okay. Anyway, so as you see from this one here, guys, this is the response. It's very clear that, by the way, when you can see here, uh, in this figure here, you can see at small frequencies, because you can see here, this one is actually 1 plus omega c r squared. Okay, this is, we got it from here. Okay, in case of small frequencies, this omega c r squared much smaller than 1. So this part here becomes equal to 1. Okay, this is what happened in the beginning here. So in the beginning here, actually omega c r squared is actually less than 1. Okay, and now log 10 of 1 equal to 0. Okay, 0 decibel. Okay, that's why you can see here, this is 0 decibel, regardless of what frequency we have here. However, as we increase the frequency now, this part, we cannot ignore this part anymore. Okay, what happens at high frequencies actually, so this part is WCR square is actually much greater than 1, and this is how the equation looks like. So you can see here in this equation, as you increase omega, which actually is same thing like frequency, as you increase the frequency or omega, this value increases, and because it is negative here, so the curve will go down. It will get smaller. Okay, so as you increase omega CR square, okay, and when you take the log, and because the log is negative, so actually it's going to get smaller. So actually this is frequency response. What happens here, as we see, at a certain it's going to go this way, and then it's going to go down this way. Okay, again, this is the practical response. Ideally, as I told you before, it has to be this way. Nothing should pass here, but again, not here. This is not ideal one. Okay. There's a very important here frequency. As I told you before, we call it cutoff frequency. Here at this moment here, we call it a cutoff frequency. So we are going to assume all frequencies from here until the cutoff FC, cutoff frequency here, are going to pass. And anything greater than this one is not going to pass. We assume that, okay? And usually when I design a filter, I design a filter to give me a certain value for cutoff frequency. Okay, how can you find this cutoff frequency? Very simple. So cutoff frequency, you can see here, the magnitude or the gain drops by the value of 3 dB, 3 decibel. So here is a value of 0. Once it drops to 3 dB, okay, at this moment here, this frequency is a cutoff frequency. Why it is 3 dB? What is the reason for that? Simply because if we go, because at to get the number of 3 dB, okay, here, omega, let me come here to show you exactly what I want to say. So here, what happens here, actually omega CR equal to 1, okay, and now the magnitude of EF should equal to 1 divided by square root of 2, okay. This value here is corresponding to the moment at which the output power is going to be reduced by half of the input power. So you see here, guys, as we increase the frequency, the magnitude of the output voltage reduces, okay? The moment at which the output power is half the input power, that's what we call cutoff frequency. So what happens at cutoff frequency is the amplitude V output divided by V input should equal 1 over square root of 2 as a voltage. If you calculate the power, it will be half, because you know power V squared divided by R, so if you square V, so it's going to be half. So again, guys, let me make it simple. So how can we calculate? First, what do you mean by cutoff frequency? Cutoff frequency is the frequency we assume anything after that is going to pass, anything after that should not pass. That's why it's a very important thing to show. Number two, practically, ideally has to be something like that. And this is FEC, okay, but actually here is gonna be something like that. And then I'm gonna take, or it should be, okay, maybe more better. Yeah, something like that. So it has to be here. As you see here, we're gonna take it here. Okay. So how can we measure this cutoff frequency? Number one, if you are using, and most of the time we are gonna use decibel or logarithmic numbers. If we are doing that, see what value here, and when it drops by minus 3 decibel, the corresponding frequency here is a cutoff frequency. Same thing. If we do measurement in the coming lab, when you find V output divided by V input equal 1 over square root of 2, this is a cutoff frequency as well. Okay. So this is one thing. This is what we call frequency response. Okay. Another thing here, as you see here, the phase. Again, this is a phase between input and output. Phase between input and output. So I just use this formula here, and just I draw it so we can see, and that's what you should see in the coming lab. At very small frequencies, at these frequencies here, the phase is 0. What it means, the phase is 0. It's very interesting. So you will see the output and the output are in phase. So, okay, so they have the same phase. This is because the capacitor is almost open circuit and it doesn't have too much impact, right? However, as we increase the frequency, now the capacitor, the impedance of the capacitor decreases, and now it has some impact. So you can see here, exactly at cutoff frequency, you will find it is negative 45. This is the phase angle. At very high frequencies, you should notice it is negative 90. Okay, you know, first negative here, because this is so here, so here the out, because always this relation is negative, so always the output signal lags, because this is V output divided by V input. You see what I'm saying? Equal to negative value. So here always the output lags the input. That means what you should see, if the input is this way, the output should lag, come after. Okay, so if this is the input, this is what the output is, should lag. Okay, in the very beginning, this angle 0. Okay, after that should be negative 45. So this you should see 45. After that should be negative 90. You know what negative 90 looks like? It looks like here is 90. That means if this is the input, because here in this case the output lags, right? Yeah, the output signal lags is the input. So this is the input and the output here lags. 45 means it's gonna look, this one is gonna start from here, this one is gonna start from here. Okay, 90 means it's gonna start from here. Okay, something very interesting you need to see in next coming lab. Okay, so I told you guys, by definition, the word cutoff frequency is actually the frequency at which V output divided by V input equal to 1 over square root of 2. That's the definition. Okay, and this is the frequency at which the output signal power is actually half the input signal power. So, and this should happen here in this specific case when actually omega CR equal to 1. So when omega CR equal to 1, so V output divided by this should be happen at the cutoff frequency. So here, omega 2 by F, from here we can say F, as you see here, F should equal 1 over 2 by CR. Very important formula, because that means when I design a filter, I have to design a filter for a specific value of cutoff frequency. That's it. So all what you have to do, you have to select some value for C and R to achieve this, to achieve a certain FC. You see what I'm saying? Because again, how FC is important. Any frequency less than FC is gonna pass. Anything greater is not gonna pass. You see what I'm saying? Anyway, so yeah, here just in case if you are confused about phase, how can you measure phase? For example, as you see here, we have two signal A and B. Okay, it's very clear. So you can take any point and you compare. For example, if I take this point here and take this point here, okay, or I can take this point and the corresponding point here. Okay, you can see always the signal A is leading B. So here in this case, A leading B, or B is lagging A. Both are correct. You see what I'm saying? So in the coming labs, you have to watch for these values, as I told you. In case of low pass filter, in case of small frequencies, you need to find the relation between output and input is 0. That means you should see they are in phase. They are in phase. Okay. So, and then at cutoff here should be 45, and very high should be negative 90. And here the output lags. It's the same thing if I see the input leads. Same thing, okay? Output lags means input leads. However, as I'm going to explain in case high pass filter, actually here in small frequencies, because it has to be something, yeah, go this way. Okay, so at small frequencies here, at small frequencies, you can see it will be around negative. It's coming anyway, but just I'm going to explain it, but I just want to show you there are differences here. Should be 0 when at high frequencies. So here at high frequencies here, at this part here, the phase shift should be 0. Okay, anyway. So now I'm going to move to high pass filter, and then I'm going to repeat the same because already the idea is clear. Let me go back to show you the difference. The only difference here we put R here and C here. I'm going to switch them. That's it. That's it. And tell me how this is going to work. How this, again, this circuit should pass high frequency. Small frequency, it has to block. Before I go to the math and show it just by intuition, at low frequencies, Z should equal 1 over G omega C. Omega is small, so Z is small. Okay, so I can assume the capacitor is open circuit. So here, it's like you have open circuit here, so the signals are not going to pass. You see, this is a very simple idea. Frequencies are not going to pass, okay? However, at high frequencies, now the capacitor becomes short circuit, and now it can pass high frequencies, okay? So again, I want to do, this is by intuition, Now, if you want to do it using math, look here, it's going to be, the math we're going to see here is very close to what we did before, okay? So again, I'm going to use voltage divider to calculate this is output, this is input, this is how it looks like. But this time, because here you have ZC and here you have R, last time it was the opposite. Okay, so if you do that, you will find the gain here is similar to the previous gain. The only difference before it was 1 plus j omega c r. This time, because we switched r and c, it should be 1 over here. This is the only difference. Anyway, same thing now. If you have, this is the relation between output and input in as a complex number. Okay, if you calculate the magnitude and if you calculate the angle, this is the angle between input and output. This is the magnitude, as I told you. Why is this important? Very important, because this magnitude should tell you which this should give you the magnitude of the output at different frequencies. You see what I'm saying? So that's why when I draw the response, in this case, the response should look like something like that. I'm going to use the magnitude here. This angle should tell you the relation between output, the angle. Okay, so how this is how this one should look like. Okay, look. So see here again. At very small frequencies, it should not pass, and then as we increase the frequency at a certain point here, again, this point we call it cutoff frequency. Very important, similar to the previous one. However, big difference. In case of low pass filter, cutoff frequency, all frequencies from 0 until cutoff is gonna pass. Anything greater than the cutoff frequency is not gonna pass. Here it is the opposite, because this is high pass filter. Anything that's smaller than cutoff is not gonna pass. Anything that's greater is gonna pass. You see what I'm saying? So again, how you came up with this figure? I didn't do anything. I used this formula. That's it. But again, because I told you here, when we calculate the frequency response, we use logarithm. Okay, so that's why we calculate it in decibel, which is the same thing like this one. However, I'm gonna calculate 20 log10 instead of putting this value. No, it's gonna be 20 log10. That's why you can see here. As you see here, guys, 20 log. Again, we do that because usually frequencies are very high frequency, just to get a figure that is meaningful. I'm gonna talk a little bit about this one later, but the scale here is not linear scale, it's logarithmic scale. You will understand what this means. Just give me some time. Okay, so what happened here, this is frequencies are gonna pass starting from cutoff frequency here. How can you know the cutoff frequency? Again, at cutoff frequency, okay, the power should be half of the power at high frequencies here. Okay, in other words, if we talk about decibels, the difference from here to here in decibels, the difference should be negative 3 dB. Okay, in other words, or if it is not decibel, so V output divided by V input should equal 1 over square root of 2. Okay. So when the relation between output and input equal 1 over square root of 2. Remember, here the relation equal to 1. Here equal to 1. Here 1 over square root of 2. Okay. So and this should happen based on this formula here. Again, I want to calculate, because when I design a filter, I have to select C and R to achieve a specific cutoff frequency. Okay, so if you see this one equal 1 over square root of 2, that means this part here has to equal to 1. That means 1 over omega CR equal to 1. Okay, that means if you do it, you find F should equal 1 if cutoff frequency 2 pi RC, which is the same formula I had before. Very interesting. So if I come back here, again, if I go to low pass filter, this is the cutoff frequency is here. I have to find values from C and R that can give you a specific cutoff frequency. Same thing here. Okay. Same thing here. It's the same value, but cutoff frequency, anything greater than F is gonna pass, anything smaller is not gonna pass. And this is the phase. Okay. In the coming lab, I'm going to ask you to just focus on 3 values. At very small frequencies, you should see a phase shift of positive 90. Here, you have to see a phase shift of positive 45. And then here, you should see a phase shift of 0. Please, guys, you need to understand what I mean by phase shift. When it is 0, that means they are at the same time. There is no leading or lagging. Okay. Here, this is because this output divided by input. Here a positive, that means the output is leading. You see what I'm saying? So if this is the input, the output will be something like that. Oh, sorry. This is if this is here, this is the output. So here, this is the input. The output is, in this case, is actually lagging. So I made a mistake. So it has to come before it leading. Okay. So that's what you should see. So make it very simple. That's what you see in this lab. In case of low pass filter, you will see that if the input this way, the output always is lagging. But here all in case of high pass filter, you will see the output is leading. Okay. That's why it's positive here. Anyway. Okay. That's it. So again, guys, before I move forward, make it very simple, very simple. So all what I said, guys, number one, I defined what I mean by filter. I told you we have different types of filters. You should, we are going to only focus on low pass and high pass filters. Okay. You should understand what is the ideal, frequency response has to be this way. You should understand in reality. So it has to be, you have some frequency and then zero. In the reality, we cannot get something like that. In reality, there is, I want to cut frequencies here. Unfortunately, there are some unwanted frequencies are gonna pass. Okay. So we try to make the circuit more accurate, more complicated, so that this curve here, this line here, we try to make it closer to the ideal case. Okay. And also explained very simple. All what you have to be just one resistor, one capacitor. It can be this way. Input here, output is here. If you do that, you will find this is the magnitude, and you find this is the angle between input and output. This is how the response looks like. The second one here, all what we did in case of high pass filter, I just put C here and put R here. Okay. And this is the magnitude, this is the angle, okay? And then this is how the response looks like. So as expected, because this is high pass filter, as expected, it has to pass high frequencies and it has to block low frequencies, okay? Anyway, so now I'm gonna move to another thing, we call it active. By the way, everything I'm explaining here, we call it first order filters. First order, okay? Let me tell you here why you are calling it first order. So as you see here, guys, as you know, if you are designing a low pass filter, this is the ideal behavior. It has to be this way, ideal, okay? It has to be this way. So what happens is that, because again, this is just an introductory course, introductory lab for filters, okay? So I'm going to make a simple circuit. That's why this circuit, we call it first order. It's very simple circuit. As you make the circuit more complicated, we can make it second order, fourth order, 10 order. So you can see here, again, I'm not asking you too much. I want you just to learn that, because this introductory lab in filters, we're going to do only first order. But there is something you may learn in the future. We'll call it second order, fourth order. What happens now, we make the circuit more complicated so that the response here becomes very close to the ideal behavior. That's it. You see what I'm saying? So nothing is for free. You wanna, again, this is the ideal response. It has to be this way. Okay. Again, if you make a simple circuit, it will be first order this way. If you make a more complicated circuit, it has to come this way. It has to come this way. So the more you complicate it, you are gonna get closer to the ideal behavior. That's what we call higher order filter. This is just for your knowledge. This is an introductory course. We're gonna only focus on first order. Okay, very simple. So now this all of this, everything I explain now, first order. But what I explain right now, we call it passive. Passive. So here, this circuit is passive for high pass filter. The other one also passive. Now I'm gonna move to active. What do you mean by active, and why it's interesting? I'm going to show you what I mean by active. All what I did, look here, guys. This is the same thing I have just explained before. R and C. This is low pass filter. Okay. However, I'm going to put after it a non-inverting amplifier. In this case, we call this filter active filter. So again, active filter means this is a passive filter, but after that, I'm going to put non-inverting amplifier. Same thing if you see Nothing is difficult. Same thing here. If you put a capacitor here and you put a resistance here, this one is actually high pass filter, high pass. And then after that, I'm gonna put non-inverting amplifier. But why? Why we wanna do that? I'm gonna tell you why. Simply because number one, if you see this filter here, guys, the maximum value I can get here is 1. Sorry, the maximum V output divided by V input, the maximum value I can get is 1. Relation output input. It should happen when this capacitor is open circuit and there is no current here. So this V output should equal to V input. Okay, should equal to 1. Okay, what about if I want to make amplification? So I wanna amplify it. So I want V output to V input equal to 10, 20. You wanna amplify, it's not the maximum value equal to 1. No, I wanna amplify it. For sure, I can use amplifier here. This is the first benefit of it. The second benefit of it is actually there is a problem. Look here, if you have here R and then you have a capacitor this way, and then for sure I'm not going to use this circuit alone. There is another circuit here. The circuit here also has a resistance. This resistance is gonna be a load. You are gonna load this resistance, the filter. You are gonna load it, and then you are gonna change the cutoff frequency because it's like you added a resistance to the R and C. You see what I'm saying? But this is not the case here because actually the input current here is 0. So even we're gonna if you have another, because this is the filter. If you have another another circuit here, this circuit is you are gonna put the resistance here, so still it's not gonna impact. We're not gonna load this R and C. We're not gonna put some resistors here. You see what I'm saying? So now, in order to summarize, number one, active filters. Active filters, we use the same thing like passive filters, but here we use op amp for amplification, number one. Number two, because to avoid, if you have here R, resistance for R, if I connect it directly and you don't have this one, this R is gonna add it to the filter here to R and C, right? And it actually changes the cutoff frequency. Okay. So we don't want something like that for sure. Okay. Anyway, so you can see here, guys, this is not something very different from what I explained. I'm going to show you there is only one difference. Okay. So as you see here, guys, it's the same thing circuit. So what I explained before, this circuit here, low pass filter, I just put amplifier here after it. You see what I'm saying? So if you see, okay, tell me how this will change. Number one, cutoff frequency, because we agreed the cutoff frequency we calculated before, 1 over 2 pi RC. Does it change it? The answer is no. So even here in this circuit, it's the same cutoff frequency. Great. Number two, how this changes the phase? Nothing. It's the same phase. So again, the phase we calculated before, okay, these values for the phase are the same. Cutoff frequency is the same. The only change is very small change. The only change is, look here. Here I started from 0 decibel. You know why it's 0 decibel? Because at the start here, the gain, which is V output divided V input, equal to 1. So when you calculate 20 log of 1 equal to 0. You see what I'm saying? However, when I add amplifier after that, and so here, so it's not gonna become, it's not V output divided by V input here is not gonna become 1, like this case here. It's not gonna become 1. Okay, in decibel it is 0, but in normal values it is 1. Okay, however, this will equal to the gain of amplifier. That's it. So here you will see a different value here. So instead of the value here, this is only change. After that, everything almost is the same. Instead, what's happening right now here at this moment here, 20 log 1. That's why you will see 0 here. If you put amplifier, so it should be 20 log ADC. And ADC, this is actually the amplifier. This is the gain of the amplifier. If it is 2, just put 2. If it is 3, just put 3, and so on. So you can see, guys, everything is the same, except only there is one difference. Everything is the same. And it's, even this 3 minus 3 dB will be the same. For example, here, let me give you an example. For example, if I make the amplifier equal to 2, okay, so this one here should equal to 6 dB. Okay, positive 6 dB. And then Again, we're going to reduce by 3. So this point here at the cutoff should equal 3 dB. That's it. That's it. So instead of 0, we're going to start from the gain value. Whatever gain you have, okay, take the log, and this is your starting point. Still, if you go down by 3 dB, you will get the cutoff frequency. The only difference is everything is similar. The only difference is this value here. That's it. Best. So this time, this value is equal to, this is the amplifier value. Okay, as you will see right now. Okay. So, yeah, that's what I did. So what I did here, guys, I told you there is a gain. This is the gain of because this is non-inverting circuit, and you know, in case of non-inverting circuit, it's 1 plus R2 divided by R1. Okay. So you can see everything almost is the same, except when you, this here, remember this one was 1. Okay. Now it is not 1. It is the amplification you had. Okay. This one is the same. This one is the same. Okay. The only difference is that in this one here, this time it is ADC, which is the amplification of amplifier. It is not 1. That's it. Okay. So anyway, that is why, as you see here, when you do the circuit, you are gonna start from some value here. You are not gonna start. It's not gonna become 1. It will be some value here. Okay. Sorry, this is for high pass. Okay. Now let's go to high pass, active high pass filter. Number 1, it's the same thing. So now this is the passive high pass filter, and then I'm gonna put non-inverting amplifier after it. Okay. Why you did that? I did that for 2 reasons. Similar, I'm just repeating what I said before because it's the same thing. Number 1, I wanna, if I use this one alone, maximum I can get V output divided is 1. No, sometimes I want to amplify the signal. Okay, so that's why I put this part here. And if this part, the gain, we call it ADC, whatever the value is. So V output should divided by V input should equal ADC 2, 3, 4, whatever. Okay, this is one thing. The other thing, as I told you guys, if there is a circuit, if you have another circuit after here, and this circuit has a resistance R, this resistance R is not gonna load. Yeah, because this is going to be a problem, guys. So if you have here, if you just use a passive one and you add the resistance here, so you are going to change. So you are going to have a different cutoff frequency because you change it R. You see what I'm saying? But because of using op amp here, that's why active is better. So number 1, guys, you need that. Let me make it very simple. I explained in the beginning passive. Passive means it doesn't have an active element like a transistor or op amp. We call it active. Number 2, this one is active. I just added here op amp. Okay. And you need to know why I did that, what benefits I have here. Okay. So one more thing I want to explain to you. So now you understand it's not a big difference. So if this is a passive, I just added amplifier here. Okay. And I told you this is good for 2 reasons, as I explained. Okay. However, this one doesn't come for free. Unfortunately, there is a problem here. What is the problem here? Okay, and this is also something you need to see in the coming lab. The problem is that if this is a high pass filter, okay, in high pass filter, it has to be go up this way, and then it's going to be this way. Okay, so and then here you have to calculate the cutoff frequency, which is not at this point, by the way. The cutoff frequency should be at this value here. So some value here. This is a cutoff frequency. So maybe I made a mistake. Let me delete this one. Just to, so what happens here? If the response is this way, okay. So here, either minus dB, or if you just calculate values, when V output divided by V input should equal to ADC divided by square root of 2, not 1 this time, VTC. Okay, so here at this moment, this is what we call cutoff frequency. Okay, so the gain here is ADC. Here at this moment here, ADC divided by square root of 2. Okay, in decibel should be a negative 3 decibel. Okay, so anyway, so this is what we call cutoff frequency. So anyway, ideally, okay, I was talking about adding this op amp. There is a problem here, okay, and that's what something you need to see in the coming lab. So what is the problem? The problem is that, look here, as I told you, we are expecting that in case of high pass filter, this is, and then it's gonna go to infinity this way, infinity of frequency. Okay, yes, it has to be this way. However, because the op amp itself is not ideal, the op amp cannot be used at very high frequencies. Okay, because it's gonna fail. It has limitations. There are some maximum so what's gonna happen, what you are gonna see, what you are gonna see, look here guys, a very interesting thing you will see. So number one, I will see this one come here this way and then moving this way. Okay, great. And this part is because of the filter. The filter will do that. However, it has to go the way to infinity. It's not going to happen. I will see now something like this will happen here. Okay, is that a filter? No, it's not. Yeah, okay, you can see it like a filter, but I didn't put it. I don't want it. I didn't put it. But this is mainly because the op amp itself is not ideal, and it's not going to work at very high frequencies. So again, the op amp, because it's not ideal, is going to put a limitation on the maximum usable frequency. So you can use this filter from the cutoff frequency. It's not until infinity, no, until this value here. Okay, and this is something you need to find in the experiment. So in this experiment, you need to increase the frequency, and then until the op amp fails, or the op amp, yeah, because this part is coming from the op amp, not from the filter. Okay, it fails. Again, is that something? It's not useful, so now it's useless? No, it's not a big deal. It's not a problem. All what you have to do is that you have to make sure, yes, it's gonna work, but this is, you have to work in this range. And I ask you to find this frequency here. We call it maximum usable frequency. Okay. If in case you need something bigger frequency, okay, you need to buy a better or a high performance op amp, because this problem here is coming from it may not be a problem, guys. It may not be a problem. If again, if for example, if I start here from 1 kilohertz, okay, and then I'm going to use until 50 kilohertz. This is my application. Okay, if this one drops after 50K, okay, it's not going to hurt me. You see what I'm saying? However, if you want to make it more, so the only thing you need to do, you have to buy high performance op amp. You see what I'm saying? That's why, although I'm expecting it has to be this way, it's going to go this way. But now I'm going to give you a very quick idea. You are telling us the op amp itself is going to fail at high frequencies. Okay, what is the reason for that? Okay, here I'm explaining quickly the reason, because also is something interesting to learn. Number one, there is something we call a slew rate. You see, slew rate. This one should tell you maximum rate of when at high frequencies the input are going to change fast at high frequencies, because of the internal capacitance of the op amp. The op amp the output cannot change as fast as the input. Okay, and this will cause the signal to be distorted, and this is something you should see in the lab. So in the coming lab, you will see in the very beginning the output is very nice. However, as you increase the input, you will find the output started to be something distorted. Distortion happens. Why? Because the input is changing too fast, and the output is not able to track the input. This is because of the op amp. Again, guys, this can be a problem or may not be a problem. If you want to use the op amp before this frequency, okay, it's not a problem. I don't care about it. Okay, if you need higher frequency, something already in the op amp, you need to buy a more advanced one, or the one that has high performance. There is another reason. So this is slew rate. There is another reason here. We call it gain bandwidth product. So what happens here, guys? The multiplication. This a limitation in the op amp. When you multiply the gain times the bandwidth, it should be a constant value. Okay, that means I think I have a very nice figure to understand what I want to say here. For example, look here, guys. If I want to make the gain 100, is that okay? So that means I can use it until only 10 hertz. You see what I'm saying? That's what we call a bandwidth. Bandwidth means the maximum frequency. Okay. So if I make the gain smaller, like 40, as you see, look, I can use it until 10 to the power 4. So what I want to say is that there is a relay. As you increase the gain, the maximum frequency is gonna go down. So two problems: slew rate and also the gain bandwidth here. This is something naturally, okay? So if you calculate the gain is 2, okay, this gain should be okay, but at some frequencies it's gonna fail, okay? Because the op amp cannot be used after that. You see what I'm saying? Anyway, I'm not asking you to investigate too much this part or to think too much about it, but all what I want you to understand, uh, I'm expecting to see something like that, yeah, and this will happen because it's a filter. However, what's gonna happen at some point is gonna go down here, okay? And then this should be my maximum usable frequency. I should not use any frequency greater than that. And the reason for this part is actually because of the op amp itself is not ideal, okay? This is coming from the op-amp, okay? And this is because of two reasons. I explain them quickly: slow rate and also gain bandwidth product, okay? Slow rate again means a limitation on the maximum rate of change of the output. So even if the input change very fast, the op-amp cannot keep track, okay? Cannot change at that fast, okay? One very important thing here is that, yeah, so actually, yeah, so what you have to see in the lab, you have to see something like curve like this one, and then it's gonna go down this way. So you have to see something like that. And then you need to find this frequency. I'm gonna call it maximum usable frequency. However, be careful. I'm not saying you will get these numbers. I didn't say that. I didn't say you will get these numbers because this number depends on what kind of op-amp are using. I'm saying you will get a figure that looks like this one, okay? Anyway. Okay, so in this lab, because I know we are at the end of the semester, I did not ask you to do much in this lab. Okay, so all what I'm asking you to do, guys, number one, watch this video just to connect the circuit and find the required resistor and capacitor, make them ready, find them. Okay, and then I'm not gonna ask you to design. I'm gonna just make it very simple because we are at the end of the semester. Um, Even I'm not gonna ask you to do LT spice as usual. I usually to do that. However, if you are interested in learning how can you do LT spice for this circuit, I give you a link here, but I'm not gonna ask you to do all of that. Okay. So just because it's at the end of the semester, I'm not gonna even ask you to design. Okay. But the design should be easy because all what you have very simple 1/2 pi RC. That's it. So for a certain cutoff frequency, you need to select some values for R and C. That's it. Okay. Anyway, so this is the first circuit you have to connect. For sure, you already connected this part in lab 8, so you know how to connect this is non-inverting amplifier. Okay, so you need to connect it. This part, this is not such normal. All what we did is instead of connecting input here, no, I just put R and C here. That's it, and I give you the value of R. I give you the value of C. I give you the value of R1 and R2. So R1 equal to R2 equal to 10K. That means the gain should equal to 1 divided by R2 divided by R1. And because R1 equal to R2, so the gain should be 2. The gain is equal to 2. Okay. This one thing. The other thing here is that if you calculate that, for sure, look here. If you find the resistance here and the capacitor, this is low pass filter. Okay. When I go to high pass filter, it's going to be exactly same thing. But all what I'm going to do, I'm going to switch capacitor here. Okay, if you want to calculate the cutoff frequency, 1/2 by RC. So if I use this R, which is actually, I asked you to be 10K, I use this C, I asked you to be 100 nanofarad. If you do that, you will find the cutoff frequency is 159. That means you should see when you do the curve has to be, I'm sorry, this is this is for high pass. This one is actually low pass. So that it has to be this way, and then it's gonna go down here. So at this moment here, the cutoff frequency, this value should be 159 hertz. Okay. Very important, guys, in this lab, you have to only use ceramic capacitor because the input is EC, the polarity changes. So if you use electrolytic capacitor, you are going to change the polarity. You see what I'm saying? Positive becomes negative, negative becomes positive. So here you must use ceramic capacitors. Okay. Anyway, so now what you have to do, okay, tell me, because we're in the semester, we don't have time to learn too many things. That's okay. I know you are overwhelmed with other classes. Make it very simple. All what I ask you to do in this lab, guys, number one, to connect this circuit. Very simple. I give you all values. Very simple. So this is similar to lab 9. Okay, but you just add an RNC. That's it. Number 2, I asked you to change the input frequency and then measure the output frequency and put everything. Let me show you here. There is a table. I give you a table here. That's it. So all what you have to do in part 1, you have to change the frequency. You have to change the frequency this way and calculate the ratio V output divided by V input. You have to fill this one up and then calculate the decibel value here. So this is normal value. This is decibel value, 20 log here. Okay. And then I give you this figure here. In this figure, you need to draw. So it has to be something here, and then it's gonna it's not gonna go all the way to here because 130. Let me. I forgot 169. I guess. No, 159. So at 159, the cutoff frequency should happen. So this is 100, should be here somewhere. Yeah. Okay. So it has to be something. Yeah, that's what you have to see. Okay. But first of all, tell me where I have to start from here. Yeah, as I told you before, it should be 20 log ADC. Okay. ADC here is 2. Okay, so if you calculate 20 log 2, this should be 6.02, something like that. You have to start from 6.32, and then once it drops by 3, so by 3 to 3.02, this should be the cutoff frequency. Okay, but one more thing I want to explain to you here, guys, about this logarithmic scale. Listen to me. Usually, for frequency responses, we use logarithmic scale. Why? Because usually we go to a very high value. Okay, here. That's why. Let's see. Okay. So first of all, explain what's happening here. Okay, let's look at the x-axis here, guys. You know, in the linear scale, if you have here 1, 2, 3, 4, right? So every time I add 1. This time you don't add, you multiply by 10. So look here. So if this is 1, this frequency of 1, multiply by 10, it becomes 10, and then in multiply by 10, multiply by 10, multiply by 10. You see what I'm saying? So that's why we can use it when you have a very large scale because of frequencies, because every time you multiply by 10. Okay, what about, so from here, that's what I'm saying. So what about the ones here in these ones here? Okay, very simple. Oops. Okay, look at this ones here, guys. What happens is that, look here, we have a line here, and this is number 10, right? 10 hertz. The next line is here. Next one 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 is here. Next one. So how can I get these values? Very simple. So actually, this one you multiply by 2, multiply by 3. So this one is 10. So next line here is 20, 30. You see what I'm saying? So here between each 2 lines, we'll find 9 lines. This line here, first line here, you multiply by 2, multiply by 3, multiply by 4, 5, until last one, multiply by 9, and then we'll multiply by 10, you will get this one here. Okay? So same thing for other one, absolutely same thing. So this one here is 1 hertz. When I multiply by 2, this is 2 hertz, right? 3 hertz, 4, right? 5. So every time I multiply 1, 5, 6, 7, 8, 9, 10. Okay. Same thing here. This one is 1,000. So next one, you multiply by 2. So 2,000. Okay. 3,000. 4, 5, 6, 7, 8,000, and then 9,000, and then 10,000. So here again, you can see the big text here, the big text here. So from here you to multiply by 10. Okay, but inside here, first one you multiply by 2, multiply by 3, all the way until you multiply by 9. Last line here, you multiply by 9. Okay. This is for x-axis. Okay, so for y-axis, y-axis is actually linear. You see what I'm saying? So if this part is from here to here is 5 decibel, this is 5 decibel, linear. Okay, it's a linear. However, the value you calculated here, I'm gonna calculate it in logarithmic, which is 20 log in A output divided by A input. Okay, here I'm gonna put hertz, not log of hertz. Man, don't confuse us. Okay, I'm not going to confuse you. Make it simple. Number one, in x-axis, we don't calculate log of hertz. We use hertz. However, when I made these lines here, I made them logarithmic. So here I'm going to use hertz, not log hertz, but the scale here itself is logarithmic. I'm going to do the opposite in y-axis. In y-axis, here it's linear. So from here to here, it's 5. You add 5. The difference between logarithmic and 5, linear, every time you add or subtract. So if you go this way, you subtract. If you go down here, you subtract 5. This time you multiply by 10. Okay. So, however, the values themselves you put here, they should be in decibel or should be log. So one of them is using logarithmic scale. Actually, the values are normal, not logarithmic. The other one, you calculate the values logarithmic, and then the y-axis is linear. Okay, again, don't confuse, guys. We do that because we have a big values of resistor. Just do it. So once you have these values here, just put these values here, and then what I want you to see here in this experiment, you will see, as I told you, something like is gonna go this way. You need to find the cutoff frequency at which, so you need to find the initial value, as I told you, has to be something like 6.2 decibel. Then you have to go here until 3 decibel, and then you need to find the cutoff, what cutoff frequency. It has to be close to 159, I guess. Okay, that's it. It has to be close. Yeah, as you see here. So you need to see something like you start from 6, you go to 3, and then this one here should very close to 159. Okay. One more thing, as I told you, in both cases, you need to find the phase between input and output in case of low frequency, cutoff frequency, high frequency, and tell me if it is leading or lagging. Leading or lagging. Actually, you already know the result. If I go back here, there is a table here. I just want to verify. I want you to verify this table. That's it. So that's what you should see. That's it. So it should be easy, guys. Okay, just connect the circuit. At low frequencies, in case with low pass filter, you should see a phase angle, phase difference between input and output is 0. Here you should find it's positive 90. Okay, just make sure that's correct. That's it. And this is here between input output. Just watch between input and output. Should be easy. Just implement it. And even I told you what should you see. Just make sure and why. Actually, I explained almost everything. Okay. This is the first part in this lab. The second part in this lab is going to be the same circuit, same circuit here, but all what you have to do, just put the capacitor here and R here. That's it. And you are going to use the same values for R1 and R2, but here we are going to change the values of R and C. So here I told you here, I'm not asking to design anything because I know this lab comes at the end of the semester. Okay. So here you can see R, make it 16K, and C should equal to 10 nanofarad. Okay. And then use R1 and R2 this way. And then if I calculate this, calculated cutoff frequency should be 1 kilohertz. Okay. Just to make sure it is 1 kilohertz. So here it has to be corresponding to 1 kilohertz as you see here. Again, because here you have to start from from 6, because 6 is corresponding when your gain is 2. So if you calculate 20 log of 2, it's going to give you 6. Okay. And then that's what you have to do. Okay. And then if you go back, if you reduce it 3 dB, this is where you should find 1 kilohertz here. Okay. One more thing, what you have to do, you have to increase the frequency for sure. It has to be, ideally it has to be this way, but it's not going to happen. At some frequency, you are going to see the output signal is going to be started to be distorted. So you see the output signal is very nice sine wave. And then after that, you will see it's going to start to be distorted. Okay. So this is because of the op-amp itself. It cannot change fast. Okay. If you want to work at higher frequencies, you have to buy another op-amp. You have to buy one that's has higher performance, more expensive. You see what I'm saying? So also I'm asking you, you need to increase the frequency. You will see something is going to go down here, and then try to find this what we call maximum usable frequency. See what? So that means if I want to use this circuit with this op-amp, it is okay until here. After that, it's going to fail because of the op-amp. That's it. Make it simple. Okay. Again, same thing here. I'm asking you to calculate the gain at different values, and then I give you this figure here, guys, to to draw the figure, for sure you will see, as I told you, it's 1 kilohertz, right? So you see a figure something like what? Because this one here, yeah, something like that. At 1, right? At 1 kilohertz cutoff frequency, and then at some point here is gonna go down. Okay. It's gonna go down. So you need to find at what values here is gonna go down. That's it. So you need to measure the cutoff frequency and you need to measure the maximum usable frequency. That's it. So again, guys, I know we are at the end of the semester, so that's why I'm not gonna ask you one more thing. I'm not gonna ask you to make a report. Okay. What you have to do, let me go to the lab. I want to show you something here. Yeah. Yeah. So if you see here, guys, in this lab, let me go down here. Yeah. So here, all what I want you to do, guys, in this lab, you don't need to make submission, okay? Because we don't have time, okay? All what you have to do, you have to print, we call it grading sheet. You have to print it before you come to the lab. And then the first thing you have to do, you have to watch this video to understand the lab. This is number one. Number two, you have to print this grading sheet, which is actually has 1 page, 3 and 4 pages. Okay. Number three, after that, when you go to the lab, as I told you, you have to just you have to put this circuit. Okay. I give you all the values. Just change the input, change the output. Change the input and measure the output, and just fill up this table. Okay. And then draw the circuit here, and then find what is the cutoff frequency. And then you need to just observe at low frequencies, what was the phase between input and output, okay? And also at cutoff, what was the phase? And high frequency, what was the phase, okay? And you should notice, is the output leading or lagging? I already explained that you already have the values. I want you just to observe, to understand it, okay? Same thing for high pass filter, okay? You have to put all values here. The phase should be here. So all what you have to do, connect the circuit, change the frequency of the output, and see the input, measure the output, and watch for the phase, okay? That's it. Draw it here. And again, for this one, in case of high pass filter, it should once it should here once at high frequencies, it should fail. This is because of the op amp itself. Okay. And so you need to figure out what is the maximum. If you want to use this filter, okay, as a high bass filter, what should be the maximum frequency I use? Because of the op amp. This is not because of the filter. If you need to increase this one here, you have to buy a more advanced, a high performance op amp. Okay. Thanks very much and good luck.